Jai Hind students, welcome to my YouTube channel. Students, life is full of upheavals. Life is full of crests and troughs. What I mean to say is that the road to success is not at all easy to navigate. But believe me students, with discipline, with hard work, with dedication and with passion, every dream of yours can come true. So with that, let's start today's session. Today students will be discussing a very interesting topic, that is relative motion, relative velocity and its various cases. We'll consider the case when the two bodies under consideration are moving along the same direction, they're moving in the opposite direction, and when the motion of the two bodies are inclined to each other, right? So in order to introduce the concept of relative velocity, let me give you an example. Students, consider two trains moving in parallel track in the same direction and with exactly the same speed. I repeat, let us consider two trains to be moving in parallel tracks along the same direction and with the same speed. Then although the two trains are obviously being in motion, it means that they must be changing their position with respect to the trees, buildings and surroundings on either side of the two trains, isn't it? But students, to an observer sitting in one train, it will appear as if the other train is at rest. But actually both the trains are in motion. It is actually the relative velocity which is zero. Clear students? So we are aware all the bodies in this universe are in motion. An object which appears to be at rest to one observer, it might appear to be in motion with respect to the other observer or other reference point. So when two bodies are considered and both are in motion, then the velocity of one object with respect to the other when both are in motion is known as relative velocity of one object with respect to the other. Actually students, velocity we are aware. Velocity is the time rate change in the position of an object with respect to any object which is at rest. But here both the objects are in motion. In that case, the relative velocity, say, of object A with respect to another object B, which is also in motion, is the rate at which body A changes its position with respect to body B. That's relative velocity. Clear students? So basically, we will make use of vector algebra so as to discuss all the possible cases, right? And it is very difficult to determine the rate of change of position of an object with respect to other object which is also in motion. So what to do is we make use of vector algebra so as to simplify this situation. It would be very easy if we tend to find out the rate of change of position of an object with respect to some other object which is at rest. So in all these three cases, using vector algebra, we will try to bring the other body at rest and then find out the rate of change of position of the first body with respect to the other body. Right students? So again I repeat, the same example regarding the train which just now we have discussed. In case the two bodies, bus or two cars are moving in the same direction and parallel track and with the same speed, then the relative velocity is zero. To one observer in one train or bus, it will appear as if the other vehicle or the other train or bus is at rest. It is actually the relative velocity. Similarly students, if two trains are moving in the opposite direction, then to a person sitting in one train, it will appear as if the other train is moving with very high speed. But actually that is the relative velocity which gets added up. So in the same direction, the relative velocity of one body with respect to other decreases. and in case the two independent bodies move in the opposite direction, then the relative velocity of one body with respect to other, it tends to increase, it tends to get added up. That is what we will prove using vector algebra, right? So let's start with the first case. So we'll discuss the first case, which is the bodies moving in the same direction. Okay, case 1 is bodies moving in the same direction. Bodies moving in the same direction by using vector algebra, right? So what we'll do is we'll consider body A and body B. Both are in motion and both are moving in the same direction. So suppose this is the first diagram. This is body A. Suppose it possesses velocity of VA. And this is body B. It is suppose moving with velocity of VB. Clear? This is first diagram. And our objective is to determine the relative velocity of body A with respect to body B. Relative velocity of body A with respect to body B is to be determined. So student, body A is to be brought at rest, isn't it? So in the second diagram, what we'll do is, let's draw the same thing. This is body A and this is body B. It is moving with velocity VA and it is moving with velocity VB. Now what we'll do is, in order to determine the relative velocity of A with respect to B, the body B is to be brought at rest, because it is much easier to find the time rate change in the position of an object with respect to other object which is at rest. So even if both the bodies are in motion, but by using vector algebra we will try to bring the body B at rest. Now how body B can be brought at rest? Yes, by superimposing vector minus VB vector on body B. So here what we do is, we will superimpose this vector minus VB vector. Clear students? So these two are negative vectors, so when they are added, resultant will be 0. So body B will come to rest. Now look, in order to nullify this effect, the same vector must get superimposed on the velocity of body A as well. That is, in order to nullify this effect, same vector must be superimposed on body A as well. Clear students? Again, I will give you a simple analogy. Suppose x is equal to y. Now, if you add x by 1, then in order to compensate this, you will also add y with 1, so as that the result remains same. Understood, na students? So, in order to bring the body B at rest, what we have done is, we have superimposed velocity minus VB vector on body B. Now, in order to nullify this effect, the same vector needs to be superimposed with body A as well. Right, students? So, what is left is, body B will definitely come at rest. So, the third diagram. Now, this is body B, which will come at rest. No doubt regarding this. Now, this is body A. Now, VA, VB, both are oppositely directed. And we have discussed in the laws of vector addition that whenever the two vectors are oppositely directed, then the resultant is always given by the difference in the magnitude of the two vectors. And the resultant is along the direction of the dominating one. So VA is considered to be greater than VB. So resultant would be VA minus VB along the direction of VA. So if it is 5 cm, it is 2 cm, it will be 3 cm. I am talking about the length of the arrow, right? So here it will be VAB. This is read as relative velocity of A with respect to B, and that will be given by VA. Vector addition of these two vectors, plus minus VB vector. So this is the proper representation. So VAB vector, it is read as relative velocity of A with respect to B. It is VA vector minus VB vector. So this is in the vector form. It is in the vector form. It is read as relative velocity of A with respect to B, and that will give us VA vector minus VB vector. Now in magnitude, now since VA, VB and VAB all are in the same direction. Look, VA is directed from left to right, VB is directed from left to right, VAB is directed from left to right. That is, all these three are in the same direction. So since VA, VB and VAB are in the same direction, therefore in magnitude, relative velocity of A with respect to B, in this case, when the bodies are moving in the same direction, it will be given by VA minus VB. This is in magnitude. Clear, students? This is in magnitude. So simply remember this concept. Whenever two independent bodies are moving in the same direction, then the relative velocity of one body with respect to the other would be given by the difference in the magnitude of their individual speeds. Clear, students? Now let us consider some examples. Like this is one train T1 moving with 60 km per hour. This is another train T2 moving with same speed 60 km per hour. Both the trains are moving along the same parallel tracks and with the same speed. So what will be the relative velocity of one with respect to other? In magnitude, it is given by the difference in the magnitude of these two. So it will be 60 minus 60. It will be equal to 0. So it is the relative velocity which will become 0. As a result of which, to a person sitting in one train, it will appear as if the other train is at rest. So that's the reason, students. Right? While on the other hand, if this is T1 moving with 60 km per hour and this is considered to be the other train, T2. It is moving with 60 km per hour in the opposite direction. This is the second article which we'll be trying to do right now. In this case, the speed will get added up. So in this case, the relative velocity of 1 with respect to 2 would be given by 60 plus 60. So it will be equal to 120 km per hour. So in this case, when the bodies are moving along parallel tracks but in the opposite direction, then to a passenger sitting in one train, it will appear as if the other train has got a tremendous speed. Actually, it is the relative speed will get added up. So in this case, it will appear to one passenger as if the other train is moving with speed of 120 km per hour. Right? So this is case 2, when the bodies are moving in the opposite direction, which we are going to verify right now. Right? So I hope you have understood this concept. So the first article is over, right? Bodies moving in the same direction. Now let's concentrate on the second one. We'll consider the relative velocity when the bodies are moving in the opposite direction. So we will follow the same steps, we'll follow the same procedure. So we intend to find out the relative velocity of body A with respect to body B. With respect to body B. So body B is to be brought at rest, right? So case 2. When bodies are moving in opposite direction. So this is the first diagram. Suppose this is body A and this is body B. This is VA, right? And this is VB, suppose. So we are dealing with the case whereby the two bodies under consideration are moving in the opposite direction. This is case 1. Now look, as I have told you, in order to determine the relative velocity of A with respect to body B is to be brought at rest, right? So how to bring body B at rest using this vector algebra? How to do it? So what to do is, we will superimpose an equal and opposite vector on body B. So this is VA. right? Now, in order to bring the body B at rest, we will superimpose velocity minus dv vector on body B. Now, these are the two negative vectors. The vector addition will be 0, obviously. Now, as I told you in the previous case, in order to compensate this effect, the same vector is to be superimposed on body A as well, so as to nullify the effect, isn't it? So, if velocity minus dv vector is superimposed on body B, same minus v vector needs to be superimposed on body A as well. So, this is minus vb vector. So, same velocity needs to be superimposed on body A as well, right? So, what will be the resultant effect? This will be body A and this will be body B. So, this is third case. Body B will eventually come at rest. The vector addition of two negative vectors is always equal to 0. While in this case, now look, VA vector and VB vector, minus V vector, both are in the same direction. We have discussed how the vectors get added vectorially when they are in the same direction. What happens? It will get added up. So what it does is like this. It will be VAB. It will be equal to the vector addition of these two. That is VA vector plus minus VB vector. So the length of this arrow will increase, isn't it? So here in the vector form, relative velocity of body A with respect to body B is given by VAB vector is equal to VA vector minus VB vector. This is in the vector form. So in the vector form, students, whether the bodies are moving in the same direction, whether they are moving in the opposite direction, whether they are inclined, the relative velocity of body A with respect to body B would be always given by VA vector minus VB vector. This is in vector form, right? Now, in magnitude. Now let's make use of sign convention. The direction of motion of the body from left to right can be taken as positive, while from right to left can be taken as negative. So VA and VAB both are directed from left to right, so they will be taken as positive. While VB, its direction is from right to left, in a direction opposite to that of VA and VAB. So it has to be taken as negative. So in magnitude, what we get is VAB, it will be equal to VA minus VB will be replaced by minus VB. Again I repeat, why this minus sign is introduced? Because VAB, VA are directed from left to right, which is considered to be positive, while VB is directed from right to left in a direction opposite to VA and VAB. That is why it has to be assigned negative sign. So what do we get? VAB is equal to VA plus VB. So students, this is the eventual result. So what's the conclusion? Whenever the two independent objects are moving in the opposite direction, then the relative velocity of one body with respect to the other, that will be given by the sum of the magnitude of their individual speeds. Right? As I've told you, these are the two trains crossing each other, obviously in the opposite direction. One train having speed of 60 km per hour, the other train also having speed of 60 km per hour. Then to one person sitting in a train, it will appear as if the other train has crossed his train with a speed of 120 km per hour, because the speed of both the trains moving in the opposite direction will get added up. That is actually the relative velocity of one train with respect to the other train. Clear, students? So we are over with the first two articles, and remember, vectorially the representation of relative velocity of A with respect to B will remain same, whether the objects move along the same direction, whether they move in the opposite direction, or they are inclined. The vector representation of relative speed of one object with respect to other will always remain same. It is the magnitude where you need to take into account the sign convention. In the case of parallel, it will be given by the difference in the magnitude of the speeds of the two bodies. In case of opposite direction, the relative speed of one with respect to the other body will be given by the addition or sum of the magnitude of the speeds of the individual bodies. Right, students? So, case 3. Let's start with case 3 then. Case 3 is, the two bodies under consideration, they are neither moving in the same direction nor they are moving in the opposite direction. Actually, their motion are inclined at an angle theta. So, let's discuss case 3. When the motion of the bodies are inclined to each other, this is the scenario. Suppose this is body B, it is moving along this direction, and let us consider this to be body A, moving along this direction. This is body A, right? And this is a reference line which is parallel to this B, and it is making an angle theta. So, in this case, the motion of the two bodies A and B are inclined towards each other, right? The angle between them is neither 0 degree nor 180 degree. It is having some value other than 0 and 180. So, it's like this. Okay, our objective is to determine the relative velocity of A with respect to B. With respect to B. So, students, body B is to be brought at rest. And how body B can be brought at rest, we have already discussed in the previous two cases using vector algebra. The same procedure will be using over here as well, right? So this is case 1. Now case 2. Over here, students, please concentrate. This is BB vector. This is A. This is BA vector. Right? The same diagram. Now, body B is to be brought at rest. So, what to do? We need to superimpose an equal and opposite vector on body B. That is, we need to superimpose minus BB vector. Like this, minus BB vector. These are the negative vectors. Negative vectors means both are of equal magnitude but opposite directed. The vector sum would be 0. So definitely body B will be at rest. So in order to nullify this effect, if you are superimposing minus B vector on body B, then the same vector minus BB vector needs to be superimposed on body A as well, so as to compensate the effect, so as to nullify the effect, right? So same vector needs to be superimposed on body A as well, like this. This is minus BB vector. Clear, students? So, third diagram. So, this body will be at rest. Body B will be definitely at rest. Now, body A. It will have two velocities. One along this direction. This is VA. Right? And the other which is being superimposed on it. It is minus B. And students, this is angle theta. So what is the angle between these two vectors? It will be 180 minus theta. It will be 180 minus theta. This is the effective angle between these two velocities which body A will now possess, right? Okay. Clear, students? So what will be the relative velocity of body A with respect to body B? It will be the resultant of VA vector and minus VB vector, right? Now, in case the two vectors are inclined, then the resultant can be given by either triangle law of vector addition or parallelogram law of vector addition. So we can construct the parallelogram over here, right? Parallelogram means the opposite sides are equal. So this is minus VB vector and this one would be VA vector. So this one is the diagonal passing to the same point. This one will give VAB. This is the relative velocity of A with respect to B. You can make use of triangle law of vector addition as well. Look, this is minus BB vector. This is minus B vector. Consider A. This is suppose M and this is suppose N. Consider this particular triangle, right? You can make use of triangle law of vector addition. These are the two sides of a triangle taken in the same order. That is, AM vector plus MN vector is equal to, this is the third or the closing side of the triangle taken in the opposite order. That is AN vector. So what do you get? AN vector, it is VA vector, plus MN vector, it is minus VB vector, and AN vector, it is VAB vector. So what I mean to say is that in the vector form, relative velocity of body A with respect to body B will be VA vector minus VB vector. So again students, the expression in the vector form remains same in all the three situations, right? In the vector form, the relative velocity of A with respect to B would be given by VA vector minus VB vector. Now what does this mean? It means that VAB is the resultant of, or the vector addition of VA vector and minus VB vector. This subtraction can be converted into addition of vectors. How? It can be stated as the vector addition of VA vector and minus VB vector. So VAB is the vector result of VA vector and minus VB vector. That will give us the relative velocity of A with respect to B. This is students in the vector form. In the vector form. Now what we do is, let's determine its magnitude, right? Let's determine the expression for its magnitude. So for that, what we do is, you are already aware of this formula. We have derived the expression for the magnitude of the resultant when the two vectors are inclined at an angle theta twice. Once we have done during the analytical treatment of triangle law of vector addition, and second time we have done the same article while dealing with the analytical treatment of parallelogram law of vector addition, right? So here we will be making use of the result directly. So resultant VAB in magnitude, what will be the value? It will be square root of resultant of these two, which are inclined at an angle 180 minus theta. So it is VA square plus VB square. I'm talking about the magnitude, plus twice VA VB cos. What's the angle between VA vector and minus V vector? It is not theta, it is 180 minus theta. So it will be 180 minus theta. So what we get is VAB is equal to square root of VA square plus VB square over here plus twice VA VB cos 180 minus theta. It is equal to minus cos theta. That is VAB is equal to square root of VA square plus VB square minus twice VA VB cos theta. This is the magnitude of the relative velocity of body A with respect to body B when the motion of the two bodies under consideration are inclined at an angle theta. Right students? Now regarding the direction, suppose this is the relative velocity of A with respect to B. Suppose it makes an angle beta. Suppose it makes an angle beta with VA vector. Then what will be the angle beta? Beta is the angle which VAB vector makes with VA vector. So let beta be the angle which relative velocity of A with respect to B makes with VA vector. Okay students, angle beta, as we are aware, it will be given by tan beta is equal to, it will be minus VB, magnitude of this, sine the angle between VA and minus VB, that is 180 minus theta, divided by magnitude of VA plus magnitude of minus VB cos angle between again VA and minus VB, which is 180 minus theta. So cos 180 minus theta. So what we get is tan beta is equal to sine 180 minus theta is sine theta. Sine in the second quadrant is positive. Magnitude of minus VB will give us positive value. So VB sine theta divided by VA. Magnitude of minus VB would be plus VB. Cos 180 minus theta is minus cos theta, right? So VA minus VB cos theta. So this is the expression which gives us the value of beta. Beta is the angle, students, which the relative velocity of body A with respect to body B makes with VA, right? So this is the magnitude and this one is the direction. So we have discussed all the three cases. Now let us revise all the things which we have discussed in this session. So let us make a summary chart. Friends, please go through this article in detail and try to remember each and every concept and the expressions while dealing with numericals related to this particular topic. We will be using these concepts only, right? So, case 1. When the two bodies are moving in the same direction, this is body A and this is body B, then the relative velocity in the vector form, it is given by VA vector minus VB vector. In magnitude, it is given by VA minus VB. This is in magnitude. Clear? This is the formula to be used in solving numericals. This is in vector form. And this is in magnitude. Okay. Case 2. When the two bodies are moving in the opposite direction. This is VA and suppose this is VB. Here the angle is 0 degree. Here the angle between their direction of motion is 180 degree. So here again in vector form the relative velocity of A with respect to B is given by VA vector minus VB vector. So vector form will obtain the same thing. But in magnitude we are aware VB is directed in a direction opposite to that of VA and VAB. Therefore VB here is to be replaced by minus VB. So what we get is VA plus VB. This is in magnitude. Right? These are the formulas which we need to retain. Case 3. In case, what is moving like this? This is VB and this is VA. And you need to find out the relative velocity between A and B. And the angle between the direction of motion of the two bodies is theta. Then as I have told you, the body B is to be brought at rest, so minus V vector is to be superimposed over here. So the relative velocity of A with respect to B in the vector form, again, it is proved in the article to be given by same VA vector minus V vector. This is in the vector form. While the magnitude of A with respect to B is given by square root of VA square plus VB square minus twice VA VB cos theta. Remember the angle between VA VB is theta. The angle between VA and minus VB would be 180 minus theta. Right? And regarding the direction, tan beta. Beta is the angle which VAB makes with VA. So it is given by VB sin theta divided by VA minus VB cos theta. So these are the important results. So again I repeat, students, relative velocity of one object with respect to the other when both are in motion will be the rate at which the position of body A changes with respect to body B. And using vector algebra, we make use of vector algebra in order to bring the body B at rest. so that we can easily find out the rate of change of position of body A with respect to body B. Now in order to bring body B at rest, we superimpose negative vector of velocity possessed by body B, and in order to compensate this same minus V vector is to be superimposed on the velocity vector of body A as well. So that's the technique of finding relative velocity of body A with respect to body B. So for two independent bodies, I repeat, for two independent bodies, if the bodies are moving in the same direction, then the relative velocity of one body with respect to other would be given by the difference in the magnitude of their individual speeds. For two independent bodies moving in the opposite direction, the relative speed of one body with respect to other would be given by the addition or the sum of the magnitude of the individual speeds, right? And in case their motion are inclined, then the relative velocity magnitude will be given by this particular formula. And in the vector form, students, it is immaterial. In the vector form, it is immaterial whether the bodies are in the same direction or whether the bodies are having motion in the opposite direction or they are inclined. In the vector form, the relative velocity of A with respect to B is always given by VA vector minus VB vector. The relative velocity of body X with respect to body Y would be given by Vx vector minus Vy vector. Relative velocity of body M with respect to body N would be given by Vn vector minus Vn vector. Understood? So I hope, students, this session must be very useful to you, and you need to understand each and every concept, right? So that's it for this particular lecture. We'll continue in the next session. Do join me then, right? Thank you.